Well, welcome to another episode of Dr. Y. We have a new viewer question. Dear Dr. Y, why do air bubbles show up in the butterfly tubing as you are drawing the blood? Even though the needle is in the vein and no air is leaking in where the needle enters the arm, and it can even be seen several tubes into the draw. Why does this happen? Well, that is a really interesting question. And I congratulate our viewer on being observant enough to see this and to have asked the question why. The medical literature unfortunately didn't supply me with any answers, nor was the vendor able to explain it. So that's why we're dressed like this. We're going to do a little bit of science to see if we can figure this out. So in our first experiment, we're just going to take some water and try and draw it up into our butterfly to see if we see the effect. So let's give this a shot. Oh, sure enough, we see exactly what's being described. We see some bubbles in there, they're moving along, and then when we try to apply another draw, we see the bubbles happening again. So, this is good news for us. This means that everything we need to explain is entirely in water. We don't need to invoke the cellular components of blood, nor any enzymes or proteins. So what can be going on? Well, when you have a vacuum collection device, it has a pressure of approximately 0.2 atmospheres. As fluid is incompressible, that means when you apply the vacuum tube to the end of the butterfly needle, the entire length of the tubing will drop to 0.2 atmospheres initially. We know from Boyle's law that the volume of a gas is inversely proportional to the pressure. So if we drop it from 1 atmosphere to 0.2, that's a 5-fold difference, we would expect to see a 5-fold increase in the volume of the bubbles. Now, bubbles in the middle of the solution are going to be spheres, and a sphere will increase by 1.7-fold in its radius as we increase the volume by 5-fold. But most of the bubbles we're seeing aren't in the middle of the solution. Instead, we're seeing bubbles that are applied to the tube wall itself. The shape of those bubbles is far more complicated and very difficult to actually calculate precisely in a dynamic environment. However, we know that its diameter will increase significantly more than the 1.7-fold that we saw in a pure sphere. We also have the fact that we have a tube which is curved. Whenever you have a curved surface, you're going to have a little bit of a magnification effect. That magnification effect will be minimal at the center and increase as you go towards the more curved and outer portions of the tube. So for the tube of a normal diameter and of this material, and for the bubbles of the size we're seeing, in the mid portion of the tube we can expect about a 12% additional increase in the bubble size simply due to the magnification. Now, as our vacutainer starts to fill, the pressure in it will start to drop. Therefore, the pressure inside that tubing will also be dropping and the bubble will start to collapse down in size. Exactly what we're seeing. But we also saw that the bubbles are moving. But there was quite a variety in speeds. Some of the bubbles were stationary, some of them were moving at about 1 millimeter per second, and some of them were moving dramatically faster than that. How fast is the blood moving? Well, if you have approximately a 5 millimeter tube and using a 23 gauge needle, it takes about 8 seconds to fill this tube. So it becomes a simple matter of calculation. In the needle itself, blood is traveling at 25 kilometers per hour, and in the tubing, approximately 3 kilometers per hour, or about 800 millimeters per second. That's dramatically faster than most of the bubbles, and so the bubbles appear to be getting stuck on the tube wall itself. But I would go further and suggest the majority of the bubbles that we're seeing on subsequent draws are exactly the same bubbles that we saw before. Very few of those bubbles are detaching and entering into our tube. But that leads to the question, where are those bubbles coming from in the first place? Well, our reader suggested the possibility of leaks. PVC is relatively impervious to air, but there are a number of joints that could leak, and potentially around the tissue to the needle perhaps is another source of leaking. Can we sort this out? Well, yes, we could do another experiment we could take this whole apparatus and submerge it in the water. Any leaks would therefore be leaks of water. And when we do this, what do we see? Well, exactly the same bubbles. So leaks are not the explanation. So what next? Well, we know that air is dissolved in water. That's, after all, what fish will breathe. Approximately, it's 0.3 milliliters of air for every 100 milliliters of water at body temperature. Now, it might be tempting to think perhaps it's because the temperature drops when it leaves the body, and that's what causes the air to come out. But that's the opposite of the truth. If you've ever had a cold glass of water sitting on your desk, you'll realize that as it warms up, it puts out bubbles. And the reason is cold water actually dissolves more air than warm water. So temperature is not the explanation. Well, perhaps it's nucleation sites on the tubing itself which are causing the air in the water to come out. To test this, I basically used one of these butterflies, ran several hundred milliliters of water through it, and then applied a vacuum tube to it. What did I see? Almost no bubbles. So I think it might be part of the story, but I don't think this is the major part of the story. Where are these bubbles coming from? Where is that air coming from? Well, there's one more thing that we've forgotten about. When one of these tubes is brand new, it is full of air. Whenever you try and fill any device, whether it be a syringe or a piece of tubing, you'll know that you always trap bits of air, some of which are microscopic in size. And so this is the air that I suspect is actually the air that we're seeing expanding. So in conclusion, what have we got? Well, we've got the air bubbles, which are from the original air in the tube. We then apply the vacuum tube, which expands the bubbles 1.7-fold at least in diameter, with a further 12% magnification due to the curvature of the wall. The bubbles are somewhat applied to the surface of the tube, and so they're moving slightly slower, but because as the tube fills, the pressure is dropping, those bubbles appear to be getting smaller and smaller, and so it looks like they're entering our tube. But in truth, it's the same bubbles being recycled over and over and over again for what we're observing. So this was a bit of a fun question to answer, so I'm really happy you sent that. So please, if you've got any more questions, please send them along to our next episode of Dr. Y.